Hello everyone, good morning. My name is Jesse, and for this presentation, I will be discussing the philosophical question of whether unlikely events can truly be explained. Using the example of radioactive decay and the work of philosophers like Carl Hempel and Peter Rattlin, I will argue that even highly improbable events can still have meaningful explanations through science, causation, and probability. Before getting into the actual argument, I first want to introduce the central philosophical problem behind this presentation. In science, we often explain events by showing that they were expected or highly probable. But what happens when something unlikely occurs instead? In this case, I will be focusing on a radioactive decay experiment involving two atoms of iodine-123, where there is only a 25% chance that the machine makes a sound. Philosophers like Carl Hempel argued that low probability events cannot really be explained in the same way as predictable ones, while Peter Rattlin believed that they still can be. Throughout this presentation, I will be examining both views and ultimately arguing that even unlikely events can still have meaningful explanations. To better understand the philosophical issue, it is important to first understand the setup of the experiment itself. Iodine-123 has a half-life of about 13 hours, meaning that each individual atom has a roughly 50% chance of decaying during that time period. In this example, there are two atoms placed near a machine that only makes a sound if both atoms decay within 13 hours. Since the decay events are independent, the probability of both occurring is only 25%. However, the machine still makes up a sound, meaning the unlikely event actually happens. This creates the core philosophical question of the presentation. Once the event occurs, can we explain why it happened, or can we only explain the probability that it might happen? This slide introduces Carl Hempel's inductive statistical, or IS model of explanation. According to Hempel, scientific explanations work by showing that an event was highly probable based on statistical laws and strong evidence. In other words, if something is very likely to happen, then we can explain why it happened. The model also requires true premises, empirical testability, and what Hempel calls maximal specificity, meaning that all relevant information must be included. The issue is that this creates a problem for unlikely events. In the iodine-123 example, the machine only had a 25% chance of making a sound, so under Hempel's framework, the actual event cannot really be fully explained. We can explain the probability of the event, but not necessarily why the event occurred itself. Some of the major limitations of Hempel's theory appear when we apply it to rare or low probability events. Under the IS model, an explanation only works well if the outcome was highly expected from the statistical evidence. But in cases like the radioactive decay example, the unlikely event still occurs even though it's not high probability. Because of this, Hempel's model can explain the probability of an event, but not necessarily the actual occurrence itself. Another issue is that the framework struggles with quantum mechanics, where interdeterminism plays a major role and outcomes are not always predictable in a deterministic way. I also think this conflicts with common intuition, because when something happens in reality, people naturally ask why it happened, even if the odds are low. This is one of the main reasons many philosophers believe Hempel's model is still too restrictive. Railton's DMP model offers an alternative approach that attempts to solve many of these issues. Unlike Hempel, Railton argues that even low probability events can still genuinely be explained after they occur. His model separates explaining the probability of an event by explaining the actual occurrence itself. So, in the iodine-123 example, we are not limited to saying that there was only a 25% chance of the machine making a sound. Instead, Railton would argue that once the event happens, we could still explain it through the laws, conditions, and mechanisms that produced it. This model also fits much better with quantum mechanics and scientific practice, because scientists regularly explain singular or unlikely events when they're not highly predictable beforehand. Overall, Railton's theory focuses on a less pure and more achieving a deeper understanding of why an event actually occurred. There are several strong arguments supporting the idea that unlikely events can still be explained. In quantum physics, scientists still attempt to explain singular decay events and detector outcomes even when those events were statistically unlikely. Another important distinction here is the difference between assigning probability and explaining actualization. Saying that there are only a 25% chance of the machine making a sound is not necessarily the same thing as explaining why the sound actually occurred. Ratlin's model handles this much better because it focuses on the mechanisms, laws, and conditions that produce the event, rather than looking at whether the event was highly predictable beforehand. It also aligns more closely with how science operates in practice, since researchers still seek explanations for rare outcomes instead of dismissing them simply because they were improbable. Overall, these arguments suggest that the explanation should involve understanding how an event emerged from nature, even if the outcome itself is unlikely. Some of the strongest counter-arguments against my position actually come from Hempel's requirement of maximal specificity, or RMS. According to RMS, an explanation only accounts as genuinely complete if all relevant information has been included. The reasoning behind this is important because Hempel wanted to prevent partial or misleading explanations. For example, if key statistical or causal information is missing, then the explanation may make an event seem more expected than it really was. The problem is that in low probability quantum cases, it becomes very difficult to determine whether we truly have all the relevant information available. Hempel would argue that because the event was still unlikely even after including the statistical laws, the explanation remains weak. Another objection is that once an event already occurs, philosophers may simply rationalize it after the fact rather than genuinely explaining it. My overall position is that unlikely events can still receive genuine explanations. I believe Ratlin's DMP model does a better job at capturing how scientific understanding actually works because explanation involves more than simply showing that an outcome was highly probable. In the radioactive decay example, the fact that the machine only had a 25% chance of making a sound does not mean that the event is beyond explanation once it occurs. We still point to the physical laws, conditions, and mechanisms that produce the outcome. I still think that this approach aligns more closely with the scientific practice, especially in quantum physics, where researchers regularly investigate singular and statistically unlikely events. Rather than weakening philosophy of science, allowing explanations for unlikely events actually expands our ability to understand complex phenomena that do not nearly fit into strict deterministic models. Through my research, I also believe that my position fits into a broader shift within philosophy of science, from focusing on purely prediction towards focusing more on causation and understanding. Earlier models like Hempel emphasized whether an event was highly expectable, but later philosophers increasingly argued that explanation should instead identify mechanisms and structures producing an outcome. As mentioned before in an earlier slide, this is especially important in quantum mechanics, where interdeterminism exists, but scientists still seek meaningful explanations rather than treating events as completely mysterious. I also think that this approach better captures scientific progress itself, because science often advances by investigating unusual or singular observations that challenge existing theories. Another strength of this position is that it supports unification and deeper mechanistic insight across different scientific fields. Instead of restricting explanation only to highly probable outcomes, in that sense, explanation becomes a tool for understanding reality more deeply, not merely for predicting what was most likely to happen beforehand. So, to conclude, I have argued that unlikely events can still receive meaningful scientific explanations. While Hempel's IS model emphasizes high probability and high predictability, I believe Ratlin's approach better captures how explanation actually functions in science, especially in fields like quantum mechanics and the deterministic contexts. The radioactive decay example demonstrates that even when an outcome is statistically unlikely, we could still understand it through the laws, mechanisms, and conditions that produced it. Allowing explanations for rare events also encourages deeper scientific inquiry rather than treating improbable outcomes as philosophically inaccessible. Though, more broadly, this debate is indicative of a shift within philosophy of science, from viewing explanation purely in terms of prediction towards viewing it in terms of causation and understanding. Ultimately, I think this explanation should help us understand why reality unfolds the way it does, even when the outcome was not the most probable one.